All right, let's get started. Now it's my great pleasure to introduce the first speaker for this session, Goran Glavaš. Goran is a professor at the University of Würzburg. His main research interests are in computational semantics and multilingual low-resource representation learning. And today, he will be talking about on improving multilingual abilities in large language models. Please take it away.
Thank you, Yufan. Thanks for the invitation and thanks for the announcement. So I'm going to talk about what we do the most in my research lab, and that's multilinguality, but I'll talk about different types of models and their multilingual properties. So without further ado, I think we can all argue that language technology is vital for society. So if you just compare what you can do today with LLMs your everyday usage of LLMs allows you to be much more effective with a wide variety of tasks than you could before. So language technology is pretty vital. The question is what's available to you, and that critically depends on the languages that you speak. Here's just one example. I don't know if this is still the case, but a few months ago it was. So if you ask ChatGPT in a language called Igbo, spoken in the Niger-Congo region, so in Nigeria, but Niger-Congo language family, it has a non-negligible number of native speakers, 45 million. So if you asked for an explanation, detailed explanation of a Pythagorean theorem and the proof of it, what you get as a result is more or less complete nonsense in Igbo, right? Why that's so is rather obvious, and Igbo is unfortunately by far not the only language that suffers from this. So the world that we live in is massively multilingual, but the language technology is not. And if you look at the totality of all the languages in the world, which is more than 7K, of them, only a small portion, around 1%, are actually supported strongly with today's LLMs. You might find some task-specific models or something more you can do for another 3 to 4% of languages, but that's about it. Vast majority of languages in the world have zero language technology support. It's not a surprise why this is the case. It really, in a data-driven neural language modeling, the performance for language highly correlates with the amount of unstructured data you have for the language, be it the text or speech or both. And this is not particularly new, right? We've known that for quite a lot of time, and this is a blog post that I like to point to by Rich Sutton, a famous guy in reinforcement learning. And he argues that every big discrete jump and improvement that came in AI was not a result of some big conceptual innovation, but rather general methods that have been able to, use more compute. So the jump in compute led to most improvements in computer science, but in AIs in general. A question for the audience: anyone knows what this is? What this architecture is? Has an embedding layer. Has an encoder of a type. So embeddings are concatenated and then forwarded to a feed-forward layer of a kind. And then it has a decoder or a classifier head that outputs the next word. So this is an auto-regressive language model. Anyone wants to guess the year when it came out, this auto-regressive language model? 2019. 2014. Other bits? So 2003, this was the famous neural language model by Bengio. And you might wonder, how come you started hearing of neural language models in 2014 or 19 or 22? Why weren't they a thing if basically the core idea of autoregressive language modeling came out in 2003? The scale is the answer. So we didn't have in 2003 there the scale of the data and the scale of the compute. The compute was not powerful enough to train a model on large amounts of data, but even if it was, the data back then wasn't at the scale at which is today. So Today's LLMs have multiple expensive training stages. So we have autoregressive language modeling pre-training, then you have instruction tuning, then you have alignment or preference learning, and each of these training stages are becoming larger and larger in terms of data and compute. How much do you need to pre-train a competitive language model today? By competitive, I don't mean maybe competitive to the best commercial models, but let's say a meaningful open LLM. How much would you need to spend? In dollars, in hard cash, or euros? Any ideas? There's no exact number, but some estimates say at least 50 million. As academic researchers, we typically don't have that kind of money, so how do you level the playing field? So the industry can scale the compute arbitrarily. One thing that they cannot scale arbitrarily is data. So there's a lot of analysis that we're hitting a data bottleneck, that all of the data out there has been exhausted. And my argument is that this is much more so for the lower resource languages, so not for languages with lower digital footprints. So what I'm going to talk about is multilinguality in the context of three types of language models, so standard text-based language models and cross-lingual transfer. Then I'm going to show you some of our recent work on multilingual vision language models, and finally, shortly at the end, multilinguality in the context of the code tasks or with code LLMs. So, like I said, we know from a long time ago that you can see from the character on the slide that it's pre-autoregressive LLMs. So from the birth times, we know that you can do cross-lingual transfer. The idea is that you have a multilingually pre-trained language model, and then whatever task you're trying to solve, you typically have data only in English or a few high-resource languages. But because the model has been pre-trained multilingually, after I fine-tuning for the task on English data, it should magically be able to solve that same task in all the other languages it's seen in pre-training. Unfortunately, that's too good to be true. When things sound too good to be true, they typically are. So in theory, yes, it understands languages that it's in pre-training, but in practice, and this was quite an influential work from 5 years ago by Annette here, who you've met already, where we basically show that as soon as you move to a bunch of other languages over a bunch of tasks, you get massive performance drops in this so-called zero-shot transfer. So I fine-tune for the task in English, I look at inference time and the performance in other languages, and this is horrible. So a lot of work and a lot of effort went into scaling up the data for the lower resource languages at pre-training to show that we can get better representations for those languages and hence better cross-lingual transfer. What we did is something much simpler and much cheaper, and that's generally the premise that I like to have in my work. Let's do something cheap, something simple that gives you some kind of improvements. So we said, let's just do sequential fine-tuning. You can always assume that you can collect at least a few labeled instances in your target language. So after your source language fine-tuning, just do an additional small step of target language fine-tuning on a very small data set. Let's see how that works. And that actually worked much better than trying to go into large-scale pre-training and increase your corpus portion of a low-resource language. This actually, with already 10 or 50 labeled instances, we were getting pretty significant improvements. This is old, you might say. This is encoder-based. We did some work additionally where we showed that if you have these few-shot instances in the target language, actually sequential fine-tuning is not the optimal recipe. It's better to interleave those few instances that you have in the target language with your large source language training data set. There are some important caveats to pay attention to, and that's that you need at the batch level, you need to balance the losses of the two languages. Because you have a large training data set, these instances in the target language will repeat a lot because you have only few of them. But in every batch, they will be coupled. These are the low resource language target. They will be coupled with different source language instances, and that provides a type of regularization and prevents overfitting to the small size target language data. Again, you might be saying, okay, this is all old news, encoder-based models, but LLMs are arguably even more Anglo-centric because those older encoder-based models could afford to do some kind of downsampling, upsampling to change the ratio of languages in pre-training. In LLMs, you can't afford to downscale, to downsample your high-resource languages because of emerging abilities at scale. So you're not willing to sacrifice your size of English so that the proportion of Swahili goes higher in your pre-training corpus. So if this is the case, then you have a problem, and LLMs are really also Anglo-centric. Now there is more and more of them coming out being more multilingual, but the gaps in performance between English and other languages are similar or even greater than they were with the older encoder models. So in the more recent work from last year, we had an idea of how about we combine something that aligns representations well across languages with an LLM, which is very good at reasoning and has a lot of knowledge and so on, but is quite Anglo-centric. So the idea that we did was to align a machine translation encoder, so NLLB encoder here, to an LLM turned into an encoder, so LLM2 technically. Why would we do that? Well, if we can make the body of the LLM understand the input as input, the outputs of the machine translation encoder, and the machine translation encoder can understand inputs in all the languages it's been trained to, then we're kind of unlocking the LLM to understand all of the languages we can feed as input to the MT model. How do we do that? The procedure is fairly simple. It's called self-distillation. We feed the same input, same sentence or text in English. You don't need data in other languages to both the original LLM with its own embeddings and the body, and this Frankenstein model where we basically feed the input to the NLLB encoder and the output of the NLLB encoder goes to LLM2. However, of course, when you start training, your LLM2 doesn't know what to do with the output of the NLLB, right? That's unaligned. So NLLB is an open source MT model. Sorry, I forgot to mention that. So we basically force the LLM by doing LoRa parameter efficient training not to change its representations compared to the original model. So when you take the inputs from NLLB, I want your representations to still be the same as when you are taking your own embeddings from your LLM. And we do that with simple L2 loss, L2 norm, basically mean square error. We minimize the difference between the internal representations of the model in the two cases, and based on that loss, we train the LoRa's inside of the LLM. The result, we can feed now the input in all the languages supported by the NLLB encoder and essentially forward them to the LLM2 encoder. If any of you is working a bit more in multilinguality, you might say, but this is kind of like continuous translation, right? You're trying to merge a translation model with an LLM. Why can't you just do discrete translation, right? When your input is in the target language, use any off-the-shelf MT model, translate it to English, and feed English to the original LLM. So that will be discrete translation. This is what we call translate test baseline. It's a common baseline for single transfer in multilinguality. And we did, of course, compare to translate tests. So kind of our continuous translation merged into the LLM against translate on the side and then feed the English input into the LLM. And we did get consistent gains with the comparability was actually as high as it can be because we used the same encoder of the same model for our Frankenstein thing, as well as for the discrete translation, so the NLLB 600 million parameters. So this is just to show you that there are ways computationally cheaply and kind of efficiently to improve the multilingual performance of the models without going into, let me get much more data for that language and revisit the whole pre-training and spend another $50 million to get, I don't know, some performance gains in a handful of languages. Right? The next body of work where we try to improve the performance in terms of multilinguality are the vision language models. And as we're heading towards the AGI, we want models that can process input of various modalities. So from a high perspective, vision and language encompasses a couple of things. Input is either an image or a text or a combination of both. And then your model can either be an embedder, encoder, produces vector representations that capture the meaning of the text or the image, or more popularly, they can be large vision language models. So they get an instruction as well, and they need to do something based on the input image, like caption it, or answer a question about an image, or do some reasoning on the image, and so on. The third part is that you have some instruction and the output needs to be an image. That's not something that we do, that's more in the vision realm, like text-based image editing or generation, etc. So what we care about here is, of course, multilinguality, improving both encode embedding and LLMs for a bunch of languages, but we also like to revisit evaluation protocols and dehallucinate these models, but that's not something I'll cover today. How many of you know CLIP? I've heard of CLIP. Okay, almost everybody. So this is by tower or by encoder. You have a text encoder, you have an image encoder, and the model has been trained contrastively. So for pairs of images that are captions, so the text is a caption of the image, you want to get a higher dot product of their embeddings than for the non-matching pairs of images and corresponding texts. These models are still useful for all kinds of tasks, searching, filtering, classifying, clustering, and so on. But many models have been trained in the meantime, so you have a lot of readily available CLIP models, and many have claimed to be massively multilingual. So they start by, for example, initializing the text encoder with a massively multilingual encoder, like XLMR or something like that. But how do you evaluate to which extent they work? So the evaluation benchmarks that were used for encoder models are typically image-to-text retrieval or zero-shot image classification. You don't know what's in the image, you encode different words or different concepts, their text, and then you see which one is the most similar to the embedding of the image. The problem that we encountered is that most of the evaluation benchmarks were predominantly in English, and those that were multilingual encompassed a fairly small number of languages. So what we set to do is build a more massively multilingual benchmark for evaluating embedding models. But how do you do that? Here, when you're doing zero-shot image classification, you can't really use MT to create your instances in the target languages because you get errors. If you have fine-grained concepts or names of, insects, there's an insect called walking stick. In other languages, if you do MT in isolation, you're gonna get a literal translation of walking stick, and that's not how that insect is called in all the other languages. So what we realize is, well, there is a resource that's massively multilingual that actually groups concepts and that you can leverage to obtain such instances, and that's BabelNet. BabelNet synsets are derived, many of them, from WordNet synsets. And ImageNet, on the other hand, is also derived from WordNet, where for WordNet synsets you have images. So that link basically allows you to seamlessly create such a resource. And then we measure the performance of a wide range of CLIP models on very many languages, hundreds, where we group them by resourceness, basically. And you can see, unsurprisingly, that the higher resource the language, generally the better performance of the CLIP models. The next step, we wanted to very cheaply improve the performance for some of the lowest resource languages for which the performance was the worst. So what we did then, we took the image caption pairs in English, translated the captions to the target languages, and did post hoc parameter efficient tuning here, where we said, okay, feed the original input to the text encoder, feed the translation to the same text encoder, get their embeddings, and then you have the image. And then you can basically apply all kinds of mean square error objectives and combine them with contrastive objectives. I want my representation of Pepper the Aussie pup to match the representation of pepper in Yana Yaseosi, which is a translation to rosa. But I also want both of them to match the image. And if you do that relatively cheaply on consumer-grade GPUs for a day or so, for a set of languages, you get massive improvements. I'm not going to go into the details, but you can see no training is the baseline, and then the numbers with different objectives are significantly higher. That's great, but the embedding models for vision language stuff are limited in what they can do. You just get the vectors out. So they're great for retrieval or filtering or linear probing classification, but they can't do much more than that. And there are very many tasks, practical tasks, that require you to generate some kind of an answer to a question to an input that's an image. So visual NLI, where you have an image and then a hypothesis, which is text, and you need to predict whether the text hypothesis contradicts or is entailed by the visual premise. Question answering or visual question answering, so you answer questions about images. There's visual reasoning, where sometimes you need to combine information from multiple images as well, and so on. So in all of these tasks, the main kind of family of models are vision LLMs or LVLMs these days. And the idea there is to align a pre-trained image encoder, something that's been trained on a lot of images and knows how to encode semantically the images, to a pre-trained LLM. To make them communicate, to make them understand each other, you need to convert the visual tokens from the image encoder into the representation space of the LLM. And for that, this component in the middle is being used. Now, what that component really is less relevant here. People have used more involved architectures, transformer architectures before. Q-former is something that's been used a lot, but lately there has been work showing that you get almost the same, or if not better results, with a simple feed-forward module. So the point is that you need to effectively train that module, whatever it is architecturally. So step one is the so-called pre-training of the alignment module, and it's typically done just in captioning. So there are no instructions, there's just the image as the input, and the LLM needs to start generating. Once the alignment module converts the visual tokens as preceding input, as the prompt for the LLM needs to start generating the caption, and you're training on a standard autoregressive language modeling loss there on the captions. In step two comes the instruction tuning. For what? For visual language tasks. So you have a bunch of data sets around image captioning, visual reasoning, visual conversational QA, and so on. And in that step, you're basically feeding an image, or more than a single image, and instruction. So natural language instruction describing the task. Additionally, an instance, maybe a question about the images, or a prompt. And then you need to generate the expected answer. So these mixes, unfortunately, they typically exist just in English. So at the time we set to do this, to make multilingual vision LLMs, we couldn't find anything really great that was open. At the time, there was only Pali and PaliX that were from Google. They were great, but they were not open. So we set up to obtain, again, a multilingual, competitive multilingual vision language model. But again, given our very constrained setup in comparison with industry, right? So in a sample and compute efficient manner. So we wanted to train as little as possible. So we initialized our Q-former, so this alignment module, from the existing one of an English-only model. So those parameters were already knowing how to align kind of the vision to the vision tokens to the English representation space. So if we could somehow align the multilingual representations through a multilingual step 2 training, so multilingual instruction mix, then maybe we'd get a functional multilingual vision LLM. And how do you get your instruction tuning data, vision language instruction tuning data in a bunch of languages when they exist only predominantly in English? Here the MT works because these are complete sentences, complete instructions. If you take some state-of-the-art MT model, yes, it will be noisy, but it will be okay-ish for most languages, right? So when you train on that, you do get boosts. Without going into the numbers, we were competitive to Pali in some settings. When you fine-tune for the concrete task in zero shot, we couldn't get close, but the point is we did obtain a fairly competitive multilingual vision language model in only 4 days of training on 4 consumer-level cards. And then we wanted more than that. So we wanted to explore how to actually, what's the optimal recipe? So we have these 2 steps, just pre-training on captioning and then the instruction tuning mix. And how much of in each step do we need to translate? Which portion of the training budget or the training data set needs to be allocated to how many languages? How much of it can be English only? How much multilingual? And we additionally wanted to have the ability, a model that has the ability to solve text-heavy image tasks, so images that have a lot of text in them, multilingually, as another requirement. So we were basically searching for the optimal recipe, how many languages to actually train with. Do we see some kind of cursor multilinguality after we surpass some threshold? Do all of our languages start losing performance? What's the per language data distribution in each of the 2 steps, instruction tuning and pre-training? And finally, we were interested in this multilingual text and image performance. So in particular, how to improve for the non-Latin script languages. And I'm not going to bother you with what we found, but we found that typically half of your budget needs to be English. The rest of your budget, compute budget or data budget, needs to be equally split between the languages you want to support, roughly. And then we did our experiments with 2 different LLM backbones, IIXPANS and Qwen 2.5. You could redo everything now with some newer LLMs, more multilingual from the get-go, probably get better results. And we grouped then the evaluation languages into different tiers from T1 to T5, where T5 are the highest resource languages and English separately, and then T1 are the lowest resource languages. And with the Qwen backbone, we could basically across the board, looking at all the results, get a state-of-the-art open, massively multilingual vision LLM. So Centurio will be presented at ACL now, so you're welcome to visit, and Gregor can tell you more about it, the main author. We also, the demo is online, so you can take a look for yourself. Here's the QR code, and I think the slides will be made available later somewhere as well. Okay, finally, just a bit more advertising for the ACL to come. We also wanted to be able to evaluate vision language models on more languages than what the current benchmarks would allow, and that's somewhere around 100. We wanted to get beyond 100 languages. So what we again found is a cheap trick how to make a vision language benchmark for that many languages. So there is a data set, SIB, which was derived from the multi-parallel Flores data set. It covers 200 languages. It contains sentences in there. It was used for MT primarily. What they did in SIB is label those sentences for 7 high-grained topics like sports and others, sports, geography, and so on. What we did then is fetch a set of images, 10 images for each of those labels. And then we were basically testing the LVLM models, whether they can match images and sentences that are on the same topic, right? Without saying which topic it is. And that basically allows you to finally evaluate the state-of-the-art vision language models on more than 100 languages, in our case, on 200 languages. Now, of course, you might wonder, is this even a relevant task? Is it a valid task? Is it a good benchmark for multilingual LVLMs? So for the languages that are covered by other benchmarks as well, we correlated our results of the models on our benchmark, and those other benchmarks and the correlations are high, which basically means for languages that are covered in the other benchmarks, our benchmark is as indicative of LVLM's performance. And now we bring you 100 more languages in which you can evaluate and test the performance. Okay, I think I have some a little bit more time, so I'll tell you a little bit about multilinguality in a fairly different setup in code LLMs. And now the multilinguality I'm talking about is the plurality of the programming languages you work with. So I'm pretty sure that many of you use code LLMs or something like Copilot. Who uses Copilot regularly? Okay, half. Let's say half of the room. Those who don't and do code, I definitely recommend using it. It will boost your productivity. You can also learn a lot along the way. You can ask questions, why is this like that? And so on. But they definitely boost productivity of software developers. They're general purpose LLMs. They're great at code generation and code cast. They're also specialized code LLMs that for certain types of tasks can get even better. And the problem with code LLMs is a very similar one in nature as with the multilingual natural language models, and that's the skew distribution of data across different programming languages. It's even worse. On the left side, in yellow, you have the distribution over programming languages. You can see that distribution is even more skewed than the distribution for natural languages, for the top 30 languages. And it's been observed that in code LLMs, you get huge performance drops for those programming languages that are less represented in the pre-training corpora, no surprise there. For example, Guadal found that they perform for bash scripting 30% lower than in Python, right? Python and Java and the highly represented languages are where the code LLMs show the best performance. Again, unsurprisingly. So what we wanted to do is find a way, again, a fairly cheap way to improve the performance for those programming languages, and that's collaboration with Irina here and a PhD student of hers, where we decided to use intermediate representation. Unlike in natural languages, in programming languages, there is a grounding, there is this interlingual. So you have compilers who, for very different programming languages, can compile it into the same intermediate representation from which then it's converted into executable code. What we use is one particular intermediate representation. There are different ones, LLVM, so low-level virtual machine. And here's an example of one simple source code in C. And here is its transpilation or compilation into the LLM VR. So what we sourced was a bunch of self-contained files that are runnable, executable programs. We compiled them with LLVM into this IR representation. We obtained pairs of source code, IR code, training instances. And then we did causal language modeling. We concatenated them, source code tokens, intermediate tokens, and then we did language modeling on such pairs. We, of course, validated that pairing them together is the critical component. You can't just randomly shuffle the IR code and the original source code, and that actually gave a lot of boosts on quite a lot of standard benchmarks for code LLMs on coding tasks like Multiply or Codex Glue, and so on. In particular, on multilingual code generation and code understanding benchmarks, quite substantial gains. Okay, so let me conclude in a more optimistic tone than what I started with. So I started with a better lesson. So is the scale the only answer to be competitive? Well, if you only care about English and solving IMO, getting a gold medal in the International Mathematical Olympiad with your LLM, then you need a scale. So you can get quite a lot from pure scale alone without too much conceptual innovation. But if you can't scale things up or you're interested in things where you have clear limitations in terms of data, then what are the actual options? So scaling the data is much harder than scaling the compute. LLMs are great generalizers, but they're worse than task specialized model if you care about precise performance on a particular task in a particular language. So those are the areas where it's still, I think there's a lot of space, a lot of room for conceptual innovation. And multilinguality in particular is something that opens still a lot of possibilities because of the clear fact that the data for a bunch of languages, for most of the languages in the world, is a primary bottleneck to coming to the ChatGPT performance for high resource languages. And there, in particular, then there is much more room for all kinds of innovative knowledge transfer techniques, looking for some kind of shared representations that you can ground stuff in. Again, much easier for programming than for natural languages, but and searching for good inductive biases, right? The basic tenet of machine learning is that if you don't have much data, then and you need better inductive biases so that you can learn from fewer data instances. So maybe we can find better inductive biases for low resource languages. With that, I conclude my talk and happy to have a discussion.
All right, thank you so much. Is there any questions? We have some time.
Thanks, Goran. I have a question about the claim that code LLMs help software developers. I've heard sometimes they help and sometimes they do not. So I was wondering if you're willing to make this claim softer.
Yeah, so I think they do help boost productivity for, let's say, common tasks, right? Common coding tasks or common coding problems. I've read a comment by GitHub CEO a few days ago, just a popular newspaper article that said that LLMs will take over a lot of jobs for average coders, but will make the top coder jobs even more attractive, right? So top software engineers, their jobs will be even more precious because when LLMs are wrong in code generation, they're not obviously wrong. So they're wrong in a very convoluted way. You need to have very high expertise to spot those errors and prevent.
But I wonder, how can I develop this strong expertise if I never get a chance to do simple coding?
That's a catch-22, yes. That's a catch-22. We will have many software engineers going into, like, hey, let my LLM do a lot. So I think the way we should use code LLMs is basically to learn from them on simpler coding tasks. So not just generate me the code that does this and then that's it. Great, I use that as a solution. But why is this like this? What does this do? Why don't you do it like like they do open a possibility to interact with them, and I think that's the way to use them, to actually use them to learn yourself. Because we need humans that will ultimately, we need some amount of humans that will be better than LLMs at coding. Otherwise, who's gonna give oversight over what the LLMs generate as code? Yeah.
Thank you.
It's maybe a little off topic, but is it possible to include sign language or some sort of sign language, like American Sign Language or German Sign Language, into LLMs?
Yeah, I've actually seen papers, and I can't remember where. We haven't done any work on that, but there is work that tries to, I think, primarily transcribe. So they take videos and they are trying to. So it's more challenging, obviously. So you need to segment the video, isolate individual gestures or signs, and then transcribe them into something that's text format based, have special tokens basically for that in order to. If you want to train on that, right? So, but I think again, I don't know much, but I think that is an area of research, and there are papers on trying to do that. Yeah.
Any more questions? Let's thank the speaker. So,